Good morning, students. Today we are going to discuss about P block elements, part 1. There we are going to discuss group 13 elements. In that, today's our latest topic is higher diborane. We have already discussed about diborane, that is B2H6, the first member of BN plus 4 series, that is B2H6 diborane, and which has two centered, two electron BH bonds. At the same time, it also has two three-centered two-electron BHB groups also. Two-centered two-electron BH2 groups. At the same time, two three-centered two-electron BHB groups this diborane molecule has. And to discuss about the structure and the bonding of higher boranes, in addition to two center two electron BH bonds and three center two electron BHP groups, other three groups are also required in the case of higher diboranes. Now let us see what are the other groups. They are two center two electron BB groups, three center two electron open BBB groups, that is three boron atoms, and three center two electron closed BBB groups. This is open BBB group, this is closed BBB group, and the other one is BB group. So apart from these two types of the bonds, the higher diboranes also have such type of three other groups. Now let's discuss about higher diboranes one by one. They are the first higher boranes. They are the first one is tetraborane. Tetraborane 10, it is B4H10. So this is a simple hydride of boron which contains three types of bonds. Three types of bonds in tetraborane. The three types of bonds are terminal BH bonds, that is two center two electron BH bonds, bridge BHB bond, that is nothing but three center two electron bond, and direct BB bonds. Direct BB bonds. And as already noted, it is formed by the slow decomposition of diborane. That is, this tetraborane is obtained by the slow decomposition of diborane. This we have discussed in the properties of diborane. Now, tetraborane undergoes both symmetrical and unsymmetrical cleavages. It has two types of cleavages in its molecule, that is symmetrical cleavage and unsymmetrical cleavage. In symmetrical cleavage of tetraborane, BH3 groups or moieties are obtained. And while in the unsymmetrical cleavage, BH2 moiety is obtained. So, in symmetrical cleavage, BH3 groups are obtained, and in unsymmetrical cleavage, BH2 groups are obtained. In the case of B4H10, that is tetraborane cleavage. Now let us see the B4H10 molecule, this one. Okay, B4H10 molecule. Here one B should be there. So boron, boron, boron and boron. Four borons. Okay, these are the three hydrogens. Here three hydrogens. And here two hydrogens, here two. These are the two BH2 groups. This is one, here B should be there, one BH2 group, another BH2 group, and this is three hydrogens attached to this particular boron and this boron and this H. This is BHB bridge, and here BHB bridge, and this hydrogen is directly attached to this particular boron. And here, apart from BH2 group and BHB bridges, it also has a separate, a special bond, that is BB bond. So this is BB bond. This is B4H10 structure. B4H10. So here we did not show H hydrogen atoms here and here. Okay, these are the four hydrogens here. BHB bridge bond, BHB bridge bond, BHB bridge. Here also BHB bridge. That is nothing but three center two electron bond. And these are the simple bonds, that is two center two electron bonds, BH2 group. Here also two center two electron bonds, BH2 group. And this also two center two electron bond, two center two electron bond. And this BB bond is also two center two electron bond. This is a simple bond called a simple covalent bond. So It has two BH2 groups, one here, two BH2 groups, and this is one BHB bridge, second one, third one, and four BHB bridges, and one BB bond, and the center boron, this one, it also has a BH bond here, one BH bond here, one BH bond here. So this is the structure of B4H10, that is tetraborane. Now let's discuss about next higher borane, that is pentaborane. Pentaborane. Pentaborane, and this also consider the series of BN plus 4 type, BN plus 4, that is B5H5 plus 4. We saw this is B5H9, pentaborane 9. So here, uh, in the case of this pentaborane, this generally in the case of boranes, they may be considered as the fragments of B12, that is icosahedron. Regular icosahedron of atoms has 20 faces, each of which is an equilateral triangle. Okay, so each of the boron atoms in the framework is attached to a hydrogen atom and forms the terminal BH bond. The icosahedron involves several canonical forms. It has number of canonical forms, and if all the vertices of icosahedrons are occupied by boron atoms, the structure is also called closure structure. So pentaborane, it has a structure called closure structure. The fragments of icosahedrons that result if we remove one or more boron atoms from a vertex or more vertices respectively are known as nido or arachno. Nidoborane or arachnoborane, okay, or other types of the structures. So closure structure, nido structure, or arachno structure, okay. And then the loose valences around the opening are sieved up by extra hydrogen atoms. The number of framework electrons for the closure series is equal to 2n plus 2, and for nido series it is equal to 2n plus 4, and for arachno series it is 2n plus 6. These are the number of electrons, framework electrons. Okay, besides this series, hypo series and clado series are also known. So closure series, nido or arachno series, and we also have a clado series, and other one is hypo series for such type of boranes, higher boranes. Now, if we consider this B5H9, it has a nido structure that obeys the framework electrons formula 2n plus 4. Nido structure, it obeys this type of the framework. There are 5 terminal BH groups that contribute 10 electrons, BH bond. This is simple covalent bond. It has only 2 electrons. Therefore, it contributes to 10 electrons. 2 electrons for BH group. Each BH group or each BH bond, 2 electrons. Therefore, 5 such type of terminal BH groups are present. Therefore, total 10 electrons. And 4 hydrogens, they use each hydrogen atom has 1 electron. Okay, so this you have the loose valences around the opening. So the making up of the framework electrons to 14 corresponding to 2n plus 4. That is 10 electrons from BH groups and 4 hydrogens. They are loosely held and each one has 1 electron. Therefore, altogether 10 plus 4, 14. That is 2 into N is number of boron atoms, that is B5. B5 there, therefore 2 into 5 is 10 plus 4, 14 electrons. Okay, so here since N is equal to 5 in pentaborane, so pentaborane B5H9. So this corresponds to 7 electron pairs, that is 14 electrons in the sense 7 electron pairs, and therefore the geometry B5H9 would be derived from 6 vertices, that is a closed-octahedron structure. It has a closed-octahedron structure. The structure thus is a square pyramid nido form derived from the closed-octahedron by removing one boron atom at the vertex. Okay, so octahedral structure, it will be having 6 vertices. Therefore, from one vertex the boron atom is removed, then we will get this nido structure. Okay, So see, close octahedron, six vertices will be there. From one vertex, one boron atom is removed. Then we will get nido structure of uh, the B5H9, that is pentaboron. The extra four hydrogen atoms form bridges across the open edges as given here. You can see here. Okay. So this is octahedron structure. One vertex here, B atom is removed. Therefore, only 5 boron atoms. Okay. So this is BHB bridge, BHB bridge, B, and here BH bond, here BH bond, BH bond, BH bond, BH bond. Okay, here one more BHB bridge, 1, 2, BHB bridge. Okay, so this is a nido structure of B5H9, B5H9 nido structure. This contains BBB bonds. BH2 groups are present, BHB bridge is also present, and BBB. Okay, BBB bonds are also present in this structure. Now, let's see the preparation of higher boranes. Higher boranes are obtained when a mixture of diborane and hydrogen is circulated through a glass tube. This is diborane, this is hydrogen, circulated through the glass tube at about 200 to 250 degrees centigrade. Pentaborane B5H9 is obtained in a good yield. So B5H9, that is pentaborane, is obtained by passing a mixture of diborane and hydrogen through a glass tube which is heated to 200 to 250 degrees centigrade. Next, properties of higher boranes. Higher boranes, they have different properties. Here B5H9, that is pentaborane we considered. This is C3H4. This is nothing but propyne. Propyne, in presence of AlCl3, if it is treated, we get this compound. Okay, this compound there, one hydrogen atom is replaced by a C2H5, that is ethyl group. Okay, next one, this is reduction. B5H9, it is reduced with lithium hydride in diethyl ether as a solvent. Then we get this substance. Okay. Next one is B5H9, that is treated with sodium amalgam in diethyl ether solvent. We will get this compound, that is disodium pentaborane. Okay. And next one is B5H9, if it is treated with lithium metal. It is treated with lithium metal in liquid ammonia. Then what happens? We will get Li2B5H9. Li2B5H9. So these are the different properties of higher boranes, that is pentaborane. Now let's see the few uses of this higher boranes. Among the boranes, diborane is the only frequently used borane. We know it is used as a rocket fuel, we said. All the other boranes may also find certain uses. So what are the important uses of diborane? Let us see. So it is used as a catalyst in polymerization reactions, and it's used as a reducing agent in the organic reactions, and used for welding torches. Next, diborane is used for preparing substances such as high energy fuels and propellants. Next, hydroboration is a useful method for the preparing hydrocarbons. Hydrocarbons, alcohols, ketones, and acids, etc. Where hydrogen, that is, these diboranes, they act as reducing agents. Next compound of 13th group is borazole or borazine. Borazole or borazine. Now, let's see the preparation of borazole or borazine. Here, borazine can be prepared by this three methods. There, the first one is by heating a mixture of boron trichloride and ammonium chloride. This is boron trichloride, this is ammonium chloride. And the initial product, that is trichloroborazine, is obtained, which is reduced with sodium borohydride NaBH4 to get borazine or borazole. Borazole molecular formula is B3N3H6, and this is obtained when BCl3 and ammonium chloride mixture is heated to 415 to 425 Kelvin temperature. Then initially we get trichloroborazole. This trichloroborazole, it undergoes reduction with sodium borohydride to give borazole. Next preparation by heating diborane with ammonia at high temperature. So when diborane is heated with ammonia at about 473 Kelvin temperature, then what happens? We get borazole B3 and 3H6 is obtained in this reaction plus H2. Next preparation, it is obtained by heating a mixture of lithium borohydride LiBH4, lithium borohydride and ammonium chloride in vacuum at about 3 to 30 degrees centigrade. So ammonium chloride and lithium borohydride. On heating this mixture to 230 degrees centigrade, we get B3 and 3H6. Other products are LiCl and H2. So B3 and 3H6 is nothing but borazole or borazine. These are the three preparations of borazole. Now let us see the properties of borazine or borazole. This borazole is a colorless liquid having boiling point around 64.5 degrees centigrade, and it has a superficial resemblance to benzene and resembles in some physical and chemical properties. Because of that reason, this borazole is also known as inorganic benzene, as it resembles benzene in its structure and properties. And it is more reactive than benzene on account of polarity of N and B bonds. In benzene molecular formula is C6H6. There CH bonds and CC bonds are present here. In the ring, nitrogen to boron bond is present. This is a coordinate covalent bond. Thus, it adds three molecules of HCl and methyl alcohol, H2O, methyl iodide, etc. And because of this particular polar nitrogen and boron bond, which is present in borazole. In this, what happens from these reagents, generally the more negative group from this reagent, it adds to boron atom because it is less electronegative when compared to nitrogen. Let's see the structure here, reaction here. This is borazole with HCl. So in this reaction, what happens? Addition takes place. From this reagent HCl, the negative part is chlorine. It goes to boron, and the positive part of this particular reagent hydrogen, it goes to nitrogen. As this Cl is more electronegative, it goes to less electronegative boron in during the addition of HCl to borazole. This is the product obtained. And the next one is borazole. It decomposes slowly and standing and undergoes hydrolysis at high temperature. So it is less stable, we can say, and it decomposes slowly. And in presence of water, it undergoes hydrolysis on heating, that is at high temperature, to form H3BO3 or BOH taken thrice, that is known as boric acid. And the product is ammonia in this. And here, let us see the structure of borazole or borazine. Structure of borazole or borazine. This is benzene. CH, 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 CH. So alternate double bonds. This is benzene C6H6, and similar structure borazole has, where this ring comprises of boron, three boron atoms, 1, 2, 3, and three nitrogen atoms. Alternate double bonds are present, and each boron has one hydrogen, and each nitrogen atom also has one hydrogen attached to it. So this is B3 and 3H6, that is borazole. This is C6H6, that is benzene. So in this borazole, it resembles benzene in its structure, and at the same time it also has certain physical and chemical properties similar to that of benzene. Because of that reason, borazole is also known as inorganic benzene. So the structure of borazole is similar to that of benzene, and it is also isoelectronic with benzene. So the number of electrons present in benzene are equal to the number of electrons present in borazole also. Okay, so therefore it is isoelectronic with benzene. At the same time, it resembles benzene in its structure and properties. Thus, this borazole is also known as inorganic benzene. Now, see the structure explanation here. It's a planar molecule in which B and N, that is boron and nitrogen atoms, are sp2 hybridized like that of carbon in benzene. And the difference is that in borazole, the pi bonding is additive and arises from the overlap of empty p orbital of boron atom with filled orbitals of nitrogen. So, in this dative bond in between nitrogen and boron, nitrogen is the donor atom and boron atom is the acceptor atom. This boron atom, it has an empty p orbital and nitrogen has an extra electron pair. Thus, the 6 electrons in the pi orbitals of borazole are defined from uh, 3 nitrogen atoms of borazole only, and that are derived from 3 nitrogen atoms and not from each of the 6 atoms of the ring, as in the case of benzene. So in the case of benzene, each carbon atoms contributes 1 electron, whereas in the case of this particular B3 and 3H6, only nitrogen atom contributes 6 electrons for the formation of 3 pi bonds. So because of the similarity of the structures of borazine and benzene, benzene is borazine or borazole is also known as inorganic benzene. We said. Okay. Next. So this is the structure, orbital structure. So boron atom has empty p orbital, 2p orbital which is empty, and nitrogen has an extra electron pair in its sp2 hybridized orbital. Nitrogen sp2 hybridized. So one sp2 orbital forms a bond with this boron, another sp2 forms a bond with this particular boron, and third sp2 orbital it forms a bond with the hydrogen atom, and the unhybridized p orbital, it has a lone pair of electrons on nitrogen, and this boron has uh, unhybridized p orbital, that is pure p orbital, which is vacant. This accepts a lone pair and this donates a lone pair. Thus, a dative bond is formed in between nitrogen and boron. Like this, 3 dative bonds are present in between nitrogen and boron in borazole molecule. Preparation of boron nitrides. Here we are going to discuss about another compound of 13th group, that is boron nitride. So how these boron nitrides are prepared, let us see. It is obtained by the action of nitrogen or ammonia on boron at 1000 degrees centigrade. 1000 degrees centigrade on heat, very high temperature. What happens? This boron, it combines with nitrogen or ammonia to form boron nitride. So this is the formula of boron nitride, Bn. It may also be obtained by heating ammonium chloride with borax. It can also be obtained. So let's say the second preparation. Native B407. So this, when treated with ammonium chloride, we get boron nitride. Boron nitride. So this resulting mass is treated with dilute HCl, in which boron trioxide and sodium chloride dissolve, leaving residue of insoluble boron nitride. So when this mixture HCl, dilute HCl, and leaving behind boron nitride. And this process is repeated again. After this process, pure boron nitride. Next preparation. It may also be prepared by heating boric oxide and carbon in the presence of nitrogen at about 300 to 1500 degrees centigrade. It is also prepared from boron halides and ammonia. So here two preparations are there. So boron oxide B2O3, when it is reduced with carbon and in presence of nitrogen, a stream of nitrogen, then what happens? It gives boron nitride. And the other preparation is from BCl3, that is halides of boron. BCl boron nitride. These are all the three different preparations of boron nitride. Now let's see the properties of boron nitride. The boron nitride resembles graphite in its crystalline structure and mechanical and lubricating properties. So it is similar to graphite in its structure, mechanical and lubricating properties. Okay, and it can withstand high temperatures up to 3000 degrees centigrade. Next, it is decomposed by heat. Otherwise, it is not reactive with the, when it is heated with acids, it decomposes. Otherwise, it is less reactive or non-reactive, and it is not changed by heating in air or oxygen or hydrogen or chlorine or iodine or carbon disulfide. So it is more stable, we can say. Here, B2O3, boron trioxide. It dissolves in hydrofluoric acid and gives ammonium borofluoride. Ammonium borofluoride. So we get NH4BF4, that is ammonium borofluoride. And the next one is when boron nitride is fused with KOH or K2CO3, KOH or K2BO3 plus NH3 and NH3 mixture. This reaction takes place. So boron nitride when treated with the KOH fused with, that is heating to high temperature. Then about the structure of boron nitride. The boron nitride has a layered lattice structure. Similar to that of graphite. Each layer consists of hexagonal arrangement of boron and nitrogen atoms. In case of graphite, all the six carbon atoms will be there. And the structure is similar to that of graphite. The layers get superimposed on one another so that boron and nitrogen atoms are alternatively above one another. And the interatomic distances of these atoms is 1.45 angstrom units, and the distance between the layers is 8.33 angstrom units. Boron nitride, like graphite, is able to act as host to intercalate the atoms, and it is able to occlude oxides, sulfides, oxyhalides, and chlorides in the same way that similar to that of graphite. Boron nitride, when heated to 3000 degrees centigrade at about 70 atmospheric pressure, it yields structure. See, this one is boron nitride structure. So these are the hexagonal rings. This is one layer. Above one layer, above this one layer, it has layered structure, graphite. And in the case of graphite, all the six are carbon atoms, whereas here boron and nitrogen atoms are present. Of graphite in two respects. So what are the differences? Let us see. Firstly, the hexagonal rings in boron nitrides are stacked directly on top of one another, whereas in graphite, the atoms of alternate layers lie between the centers of the hexagonal rings of adjacent layers. So this is the difference between the structure of boron nitride and graphite. And secondly, the atoms in successive layers in boron nitride are eclipsed, unlike in that of graphite, where they are staggered. So here the atoms are eclipsed. One boron atom of the first layer is exactly behind the boron atom. Carbon atoms are staggered, and each boron lies between two carbons in the layer. Two carbons in the layers above and below, and each carbon lies between the two borons. And it is used as an anti-sticking compound in glass makers and also for coating crucible linings since it is not wetted by molten iron. These are the uses of boron nitride. Next, let's study about the another compound of 13th group, that is boron trihalides. Boron trihalides, BX3. So let's discuss about the Lewis acid nature of boron trihalides. The relative Lewis acid character of boron trihalides is determined by their heat of formation and dipole moments of their atoms, and it is found in this order. Now let us see the Lewis acidic character based on their dipole moments and the formation of adducts with pyridine. This is the acidic nature, Lewis acidic nature order of boron trihalides. That is Bi3 is greater than, that is more acidic when compared to BBr3, which is more acidic when compared to BCl3. This is more acidic when compared to BF3. This is the order of Lewis acidic nature of these four triarylates based on values and the formation of adducts with the pyridine molecule. However, let us say the above order is just the reverse of normally accepted order on the basis of relative electronegativities of halogens. If we consider the electronegativities of halogens, fluorine is more electronegative when compared to chlorine, which is more electronegative when compared to bromine, which is more electronegative when compared to hydrogen. So fluorine being the most electronegative should create the greatest electron deficiency as boron on boron, and thus B in BF3 should accept electron pair from donor very rapidly than in other boron trihalides. So as this fluorine is more electronegative when compared to boron, then what should happen? This boron should accept a pair of electrons readily. When it accepts pair of electrons readily from other atoms, it should have more Lewis acidic nature when compared to the rest of the three. But the order is like this. Okay. So in other words, the expected order of Lewis acid strength of BX3 on the basis of electronegativities of halogen should follow this order. So BF3 greater than BCl3 greater than BBr3 greater than Bi3. But the actual order is like this based on its development values and their property. Now, this anomalous behavior we can explain on the basis of the negative tendency of halogen atom to back donate its unutilized electrons to the vacant p orbitals of boron atom. So, this we can explain with the help of an example, that is boron trifluoride. So why this anomalous behavior, the order is reversed, why it is so, that we can explain based on the back donation or back bonding of these halogen atoms with the boron atom. As halogens have they have extra electron pairs and boron atom has vacant p orbital. Because of that reason, the halogen atom present in BX3, it can back donate thus a double bond character is formed in between one halogen and boron atom in the BX3 molecule. So here let's discuss BF3 as an example, boron trifluoride. BF3 as an example. Each fluorine has fully filled unutilized 2p orbital, while boron has a vacant 2p orbital. Now, since both these orbitals belong to the same energy level, that is 2p, this is 2p orbital which is vacant 2p orbital of boron, and fully filled, completely filled 2p orbital of fluorine. 2p fluorine. Okay, so these two orbitals, they belong to the same energy level, that is 2p orbital. They can overlap effectively, as a result of which fluorine electrons are transferred into the vacant 2p orbital of boron, resulting in the formation of an additional p pi p pi, that is p orbital of fluorine and p orbital of boron, p pi p pi bond. This type of formation is known as a dative or back bonding. Dative bond or back bonding or coordinate covalent bond. We can see here. This is BF3 molecule. So one of the fluorine atom, it donates an extra electron pair to this boron. Thus, a double bond is formed. A dative bond is formed in between one fluorine atom and boron atom. Here, this is 2p orbital completely filled. That is a pair of electrons present, extra electron pair and fluorine. And this is here B should be there, boron. And this is a vacant p orbital, 2p orbital of boron. So this donates and this accepts. That's a dative bond or back bonding is formed in between fluorine and boron in this BF3 molecule. Because of this reason, the order is reversed. This one we can observe. Formation of back bonding between boron and fluorine in BF3 molecule. Thus BF bond. Okay, it has some double bond character between boron and any of the three fluorine atoms. Any of the three fluorine atoms. Either this bond may be having double bond, or this bond may be having double bond character, or this bond may be having double bond character. Okay, so boron trifluoride is the best regarded, which shows resonance. So here, resonant different structures, resonant structures of BF3 molecule we can here show. Okay. So resonance in boron trifluoride is evidenced by the fact that all the three boron and fluorine bonds are equivalent, and the boron fluorine bonds in BF3 are shorter than usual single boron fluorine bond due to double bond character or back bonding. As a result of back donation of electrons to boron from fluorine to boron, the electron efficiency of boron is reduced. Okay, hence Lewis acidity is decreased. The tendency for the formation of back bonding, that is p pi bond, is maximum in BF3 and decreases very rapidly from BF3 to Bi3 due to increase in the size of these halogen atoms. This is probably due to the fact that overlapping of 2p orbitals of higher energy levels, that is 3p in the case of chlorine, 4p in the case of bromine, and 5p in the case of iodine. So thus Bi3, BBr3, BCl3 are stronger Lewis acids than BF3. So Bi3 greater than BBr3 greater than BCl3 greater than BF3, because in BF3 back bonding is present and Lewis acidic nature of boron, the BF3 is decreased or boron is decreased, we can say. Whereas here such type of back bonding is not possible because of a larger atomic size of this halogen atoms, where the orbital, you can see here, chlorine, in the case of chlorine, the extra electron pair is present in the for 3p orbital. In the case of bromine, it is present in 4p orbital. In the case of iodine, it is present in 5p orbital. So the overlapping is not possible with 2p orbital of boron. Because of that reason, such type of back bonding is not possible in the case of Bi3, BBr3 and BCl3. Thus, Lewis acid character of halides of third A group elements decreases in this order. Boron is, in the case of other elements of third group, the Lewis acidic character is in this order: boron greater than aluminum, greater than gallium, greater than indium. So let me discuss a few questions related to this particular topic. Okay. So first one is about the borazole. Yeah, borazone or borazole. So borazine or borazole. About the borazole, they will ask the questions related to what is the structure of inorganic benzene. This is one question. Next one is write the formula of tetraborane. Another question. Why is B3N3H6 more reactive than C6H6? This is another question related to B3N3H6. And the last one we have just now discussed, that is BF3. This one BF3. About the BF3, BF3 is a weaker Lewis acid than BCl3. Explain. So this we have already discussed. This one only, BF3 is a weaker Lewis acid. Weaker Lewis acid than BCl3. Why? So this we can explain based on back donation. Next, what are hydrides? Account for trivalency and monovalency of boron, aluminum, gallium, indium, and thallium. This we can explain based on inert pair effect. Next, diboron is an electron deficient molecule. Explain this. We can explain this electron BHB bridge bonds. Next, explain the Lewis acid nature of boron trihalides. Lewis acid nature of this one only, boron trihalides. This is another question which is related to this topic. Next, um, explain the synthesis and structure of borazole. Just now we have discussed and structure. We have discussed about the borazole. Next, define boron halides. Write a note on their preparation. This is preparation and boron halides structures. Next one is explain the Lewis acid nature of boron trihalides, that is BX3. Next is the structure of describe the preparation and structure of boron nitride, BN. We have discussed about the synthesis and structure of boron nitride. Discuss the structure of tetraborane and pentaborane. Tetraborane B4H10 and pentaborane B4H10 and B4H9. That is tetraborane and pentaborane structures we should discuss. Next one is what are the industrial uses of boron nitride? This we have already discussed. Okay. And next one is why BBr3 is a better Lewis acid than BF3. We should explain why BBr3 is better Lewis acid when compared to BF3. So these are the different questions we come across from this topic, today's topic. So boron trihalides, do they act as acids or Lewis acids or Lewis bases? Such type of multiple choice questions also they will ask. And next one is about the framework of electrons in the Clozo series. Clozo series, the framework of electrons. How in the case of higher boranes, different types of frameworks we have discussed. There in Clozo series, what type of framework is present, and in Nido series, what type of framework is present, we have discussed. In Clozo series, it is equal to 2n plus 2, and in the case of Nido series, it is 2n plus 4. And for Arachno series, it is 2n plus 6 type of structure. Present. Okay, next one we can, in the case of BHB bond, bridge bond, like that of such type of questions also they will ask. That is in the case of multiple choice questions or fill in the blanks type of the question, such type of questions we will come across. So about the higher boranes. There we discussed about tetraborane B4H10, pentaborane B5H9, and next we discussed about borazole or borazine. That is how it is prepared, what are its properties, and what is its structure. Next, boron nitrides, that is BN, how it is prepared, what are its uses, what is its structure we discussed. Next, finally, we discussed about the trihalides, that is BX3 type of trihalides of boron. There we discussed the Lewis acidic nature of uh, different boron halides and their comparison. So this is about today's talk on this. We will conclude and we will continue with the next group of the P block in the next video. Thank you once again.